Mm.
So can you see the screen?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, okay. All right. So this is flow work, which we discussed in the last class. I told you that flow work is given by uh, W flow is equal to pressure into volume. So it's a product of pressure into volume. So this is required when entering a open system as well as when leaving a open system. So if we are entering a open system, this is the flow work which is required, and when we are leaving the system, this is the flow work which is required. So both sides we require the flow work actually, either to enter into the open system or exit from the open system or leave the open system. Okay. Now we are going to discuss free expansion with zero work transfer. We have already discussed a little bit about this particular process when I was discussing about the derivation of the PDV work. I told you the PDV work is only valid when there is a resistance at the boundary. Now let us see what is a free expansion actually. So let us read first of all. Work transfer is identified only at the boundaries of a system. It is a boundary phenomena and a form of energy in transit crossing the boundary. So that means work will be only observed when it will be crossing the system boundary. Okay. Let us consider a gas separated from vacuum by a partition and let the partition be removed. Refer figure A. So you can see it in this diagram. We have a gas and there is a partition here. You can see the partition and there is vacuum also on the right hand side of the partition. And you can see the boundary. The boundary is this one. This one is the boundary. The dotted line shows the boundary. So the boundary has both gas as well as the vacuum. So the thermodynamic system in this particular case is comprising of gas as well as vacuum. Okay, and outside this uh, hatching shows the insulation actually. So it's a insulated system actually. Now when I remove the partition, suppose I remove this particular partition, so what will happen? The gas will fill the entire volume. Now the question is whether any work is done or not done. Okay. So first of all, let us see the gas rushes to fill the entire volume when we remove this partition. The expansion of the gas against vacuum is called free expansion. So you should be aware what is free expansion. Free expansion is expansion of a gas against vacuum. If we neglect the work associated with the removal of partition and consider the gas and the vacuum together, as I have considered already, inside the boundary we both have the gas as well as the vacuum. As our system, there is no work transfer involved here. Since no work crosses the system boundary, in the first line you can see it here. We have already written that it is a boundary phenomena, okay, and it can be observed only when it crosses the system boundary. So work transfer is only identified when it crosses the system boundary. So in this particular case, because the system there is no transfer of energy or work across the system boundary, so there is no work transfer actually. Okay, that is the thing. And now what we can show it here is, but we can say that the initial state 1 and the final state 2, they are the equilibrium states, whereas we don't know about the intermediate states. These are the intermediate states. Infinite number of the intermediate states are there. So we don't know about that. That is why we are showing this line as the dotted line. So the process is not quasi-static process. Okay. So let us see what is the thing that we can say about this particular case. We say that the delta W is equal to 0. So that means there is no work transfer. And we, when calculate the value of PDV also, that is not equal to 0. Okay, that value is not equal to 0, but it does not represent the work transfer. Okay, PDV is a work transfer in a simple compressible system. So in this particular case, we have considered a fixed boundary which is not changing actually. So uh, if we are considering only the gas, the PdV won't be equal to zero, means there is change in volume. Okay, for the, if we consider the boundary gas and the vacuum, there is no change in the total volume of the system. But yes, the volume of the gas is changing. So, but we cannot consider it as a work transfer. Okay, this is not a work transfer, PdV. And because there is no energy transition across the system boundary, so there is no work transfer. Now let us consider the second case. In the second case, what we are considering is, we are considering only gas as the system. Now you can see the boundary is shown by the dotted line. In the previous case, the boundary was containing both the gas as well as the vacuum. So in the previous case, the system was gas and vacuum, but in this particular case, the system is only gas. So thermodynamic system is only gas. Now what happens when the partition is removed? There is change in the volume of the gas, and one is tempted to calculate the work from the expansion integral PdV. Okay, so naturally, because the boundary is moving in this particular case, and you can always calculate the value of integral PdV. But once again, this is not a quasi-static process, although the initial and the final end states are in equilibrium. Once again, the same thing I am telling you. Okay, initial and the final states are in equilibrium, and we don't know anything about the intermediate states. So work cannot be calculated from this particular relation. Okay, if you are calculating the work from this particular relation, W you are calculating from this particular relation, you cannot. The reason is very, very clear. First of all the states are not in thermodynamic equilibrium. And secondly, there is no resistance at the boundary. At the boundary, there is vacuum. So you can see here, what is the pressure which is acting here? The pressure which is acting here is zero. There is no atmospheric pressure. So when the resistance is zero, we cannot use this particular equation also. I have told you when I was telling you about the validity condition of using PDV integral. Okay. Two end states can be located on the PV diagram, and these are joined by a dotted line to indicate that the process has occurred. So once again, it's not a quasi-static process. We are joining by the dotted lines only. Okay. So I hope this is clear. Now let us consider the third case. Now in the third case, what we have done, it is similar to the second case only, with the only change that now this gas is once again the thermodynamic system. This is the thermodynamic system, and here is the first partition. So what we have done, we have kept number of partitions. So you can say infinite number of partitions to make the process reversible or quasi-static. So we can say there are infinite number of the partitions. So what we do, we remove these partitions one by one. So first is removed. So gas expands. So what happens in this particular case? Yes, we can say that it is nearly in thermodynamic equilibrium state. Then the second, then the third, then the fourth, and so on. So we keep on removing the partitions. So now we know the path actually. So now we know the path, and we can also calculate the value of PDV. Okay, we can calculate the value of PDV. But once again, is it the work? It is not the work, because when I said the PDV work is only valid when there is a resistance at the boundary, and in this particular case, there is no resistance at the boundary of the first partition. There is no pressure which is existing here. For the second partition, there is no pressure. Third partition, no pressure, and so on. So even if there are number of partitions, but at the boundary after the partitions, there is no pressure. So you will say that there is no resistance to the fluid at the system boundary as the volume of the gas increases to fill the vacuum space. So work done is by a system to overcome some resistance, which is because of the breaking of the partition. Since vacuum does not offer any resistance, there is no work transfer involved in free expansion. So basically, the title itself shows free expansion with zero work transfer. Only thing is you should understand that you won't be getting any work in this particular case. So, but you should know what is a free expansion process. So this was about the free expansion. Now I am moving to the next topic. The next topic relates to the heat transfer. Now, heat is a form of energy that is transferred across the boundary by virtue of temperature difference. So, you know that if a body is at a higher temperature, whereas the body is at lower temperature, the heat will automatically flow from the high temperature body to the low temperature body. But the vice versa is not possible. Okay. The temperature difference is the potential or force, and heat transfer is the flux. The heat transfer between the two bodies in direct contact is known as conduction. You know about it. Then there is another phenomena which is known as radiation. Another phenomena is convection. So we are not concerned about conduction, convection, and radiation here. But the next line is important. The heat, the direction of the heat transfer is taken from the high temperature of the system to the low temperature of the system. That means the heat flows from high temperature to the low temperature. And there is one more thing. The heat flow into a system is taken to be positive, and heat flow out of a system is taken as negative. So this is the sign convention. So when I say, suppose this thermodynamic system, so if heat is entering into the thermodynamic system from the surroundings, so it will be considered as positive. Whereas if the system is losing the heat is going out from the system to the surrounding, then it will be taken as or considered as negative. So that is what you need to remember actually. And we use a symbol Q when we have to write, we have to use it for heat transfer. Once again, heat is a form of energy in transition, as you have just seen when I have drawn this system. Now, suppose this is the system, these are the dotted lines which are representing the boundary. So, what happens? This is the value of Q. So, you can see the heat is actually leaving the system boundary. Okay, it's crossing the system boundary. So, it is energy in transition. It is a boundary phenomena since it occurs only at the boundary of a system. Energy transfer by virtue of temperature difference only is called heat transfer. So whenever there is temperature difference, that type of energy transfer will be called as heat transfer. Okay. Otherwise, there won't be any energy transfer. All other energy interactions are termed as work transfer. So whenever temperature difference is involved, we will call it as a energy transfer due to energy transfer, which is because of heat transfer. Okay. If any other energy interaction is there, that we will be terming as work transfer. So that you should keep in mind. Heat is not which inevitably causes a temperature rise. So it is not necessary when the heat will be transferred from a system to some other body or from one body to the other body, it's the temperature of the other body will increase. It's not necessary. For example, you know, if it is a mixture of ice and water, the temperature does not rise until all the ice has melted. Okay, so this you already know. When a temperature rise in a system occurs, it may not be due to heat transfer, since the temperature rise may be caused by work transfer also. So this is very simple. For example, if there is a system here and suppose work is entering into it, but there is no heat transfer, then also the temperature can increase. Or if work is leaving the system, work is being done by the system, then also the temperature of the system may change. So it is not necessary that the temperature of the system will change only because of the heat transfer. But the heat transfer will always occur because of the uh, temperature difference. Okay. Heat like work means we are talking about both is not a conserved quantity and it is not a property of the system. So mind it, this is very, very important. So that is why I have highlighted it in the red actually. So heat like work is not a conserved quantity because it is energy in transition. So you must be knowing about the first law of thermodynamics where we say uh, it is the conservation of energy principle only, first law of thermodynamics, that energy can neither be created nor be destroyed. But heat and work are not, does not come under that category actually. A process in which no heat crosses the boundary of the system is known as adiabatic process. This we have already discussed. Adiabatic process is one in which there is only work interaction between the system and the surroundings. So we have calculated the value of the PdV work in case of a adiabatic process, and there is no heat transfer. A wall which is impermeable to the flow of heat is known as adiabatic wall, whereas a wall which permits the flow of heat is known as diathermic wall. So these are all simple things. When you will see the video once again, you can note it down. Otherwise, it is also given in the book actually. The unit of heat is joule in SI system of units, and the rate of heat transfer or work transfer is given in kilowatt or watt. So this is the unit. This is the heat transfer per unit time, or work transfer per unit time. We say we calculate in watt or kilowatts. Otherwise, if it is either heat or heat transfer or work transfer, we can say that the unit is joules only. Okay. Now, we have just seen that in the previous lecture, I told you that work transfer is a path function. Similar to work transfer, heat transfer is also a path function. So what I have tried to show here is on the PV diagram, when we have to calculate the work, we use this particular relation, and this PD work is given by this hashed area. Okay, this is the area under the curve. Similar to this, if I am taking some other plot which is actually tx plot, x right now you don't know. If I am considering a tx plot, then the area under this plot will be representing the heat transfer actually. This will represent the heat transfer, and actually we can calculate the value of the heat transfer using q1 to 2, which is equal to integral t dx. So x at the time for the time being you don't know. I will let you know about this particular case also. What is x actually? So for the time being, you should always remember that TDX is nothing but it is actually equal to the heat transfer. So if I have to calculate delta Q, then it will be given by TDX, where X is a property. So delta Q is inexact differential. Why inexact differential? I told you already, heat and work are both energy in transition. Okay, they are not the properties of the system. They are not conserved in a system. Okay, so they are not the properties. So that is why we are representing heat as delta Q. And if you see in the book, then you can also see this particular symbol for the inexact differential for the heat transfer. And now when we write Q1 to 2, then we integrate this particular equation, then we can write either Q1 to 2, that means heat transfer for the process 1 to 2, or Q1 to, or Q from 1 to 2. So these are all ways in which we can write the heat transfer. And once again, the same diagram showing the quasi-static process, and the area under the curve is representing the heat transfer. So what I have written here is delta W, we said it is equal to PdV, and where V you know is a property. Okay, this V is a property. And similarly, we can write delta Q is equal to TdX, where X is a property. This X is a property. And when we integrate this particular equation for the process 1 to 2, we can say that Q1 to 2 is equal to integral of TdX for the process 1 to 2. Okay. Like PdV work, where V is an extensive property, X is also an extensive property in TdX. Okay. One thing I would like to tell you here is that I can also say that delta W is equal to PdV. So when I write small v, it becomes specific volume. So mind it, it is a specific volume. But W you need not to write small or capital because it's not a property. Only in case of properties, I have told you when it is a uh, intensive property, we will have to use the smaller case letters. When it is a extensive property, we will have to use capital case letters. Okay, but now in this particular case, that is why this small v is specific volume now. It is not the total volume. But if you see this particular equation here, here this V is actually capital V. So this is volume. Here it is volume, whereas here it is specific volume. So that is the difference between the two. So similarly, here when I am calculating this heat transfer Q1 to 2, it is given as TDX because here it is written in smaller. So it is a basically heat transfer per unit mass. Okay. The unit that you will get here will be kilojoules per kg. But if you are writing capital TDX, okay, so here the unit of heat transfer will come out to be kilojoules. Now, what is this X actually? That you should understand. X is actually entropy. You know about entropy. You must have studied it during your 11th or 12th class, which will be introduced after the topic of second law of thermodynamics. Right now, you should always consider that uh, X is the entropy, and entropy actually we represent by a symbol S or small s. So if I am using small s, I will call it as the specific entropy. If I am using capital S, I will be calling it as the entropy or total entropy. Okay. So capital S is total entropy, whereas the small s is specific entropy. And the units are actually, if I am taking S, the unit will be equal to kilojoule per Kelvin because the mass is not in picture. I am calculating for the total mass. If it is small s, the unit will be equal to kilojoules per kg Kelvin. So before I go into this particular slide, I would like to tell you a few more things about heat transfer. Okay, so let us see. Suppose I have told you that this diagram is TS diagram, and I have shown some process like this. Suppose this is the process 1 to 2. Now I would like to know that this S I am representing for X actually. Previously I have introduced it as X, but actually it is S. S is the entropy. So I am plotting this process 1 to 2 on a TS diagram. So this is the TS diagram. So when I have to calculate the heat for this particular case, what I can do is I can calculate the area under the curve. I can calculate the area under the curve. So this is the area under the curve, and this represents integral 1 to 2 TdS. Now I would like to know whether this heat which is the heat transfer which is taking place during the process 1 to 2 is heat supplied to the system or heat rejected by the system. Means I want to know its direction actually. Can anybody tell me?
So it is supplied.
Why?
So the temperature is rising.
Why?
So the temperature of the system is rising.
Okay, suppose if I draw the diagram in this particular fashion, then suppose this is TS diagram now. So this is the area under the curve. So temperature is decreasing now. So heat is supplied or rejected by the system. Anybody else?
Sir, it also depends on the Gibbs energy.
Okay, see, don't talk about Gibbs energy here. That you must have studied in chemistry in 12th class actually. Okay, so for here, for this particular case on thermodynamics, I can tell you one simple idea. If the entropy is increasing, I have shown this arrow. This entropy is actually increasing in this particular direction. Okay, so whenever the entropy is increasing, it means heat is supplied. So whether you talk of this particular process which is shown here, or whether you talk of this particular process which is shown in this particular diagram, in both the cases the entropy is increasing. Okay, so heat is supplied in both the cases. If I would have drawn the diagram in this particular fashion. Suppose this is the diagram 1 to 2. Now what is happening to the final entropy? This is entropy S1, this is entropy S2, but the entropy is increasing in this direction. So this area now is representing heat lost by the system. Okay, this is the heat lost by the system. So you should always remember, when S increases, Q should be positive, and when S goes down, Q is negative. That means it is heat leaving the system. Positive means heat supplied to the system, and negative means heat supplied by the system. So that is what you need to understand actually. Otherwise, you can always calculate the value of the heat transfer from the relationship delta Q is equal to TdS. Okay, that is the only equation that you need to remember. Now, since heat transfer is path function, so the amount of heat transferred when a system changes from state 1 to 2 depends on the path the system follows. Okay, so it is one and the same thing as we talked about in the case of work transfer. Delta Q is an inexact differential, does not depend on the end states. So because it's a path function, it will not depend upon the end states. It depends on the path which is followed, and this is the relationship which you need to remember. This S is nothing but S. Or if I have to calculate dx, then I will get this particular equation where this x is once again S entropy. Now entropy, as you know, this entropy is a property. Okay, this is a property, and this delta Q is a path function. This is a path function. So how we can get the change in property from a path function? That is shown in this particular equation. So what we have done, we have multiplied this delta Q by an integrating factor which is 1 by T. So to make delta Q integrable, that is an exact differential, it must be multiplied by an integrating factor which is, in this particular case, is 1 by T. So I think this is clear to you now. That means, once again I will tell you here, when we write delta W is equal to PdV, and I have to calculate dV, then I say 1 by P into delta W, and if I have to calculate ds, I will say 1 by T into delta Q. So now this is a property and this dV is also a property, so I can calculate the change in property by multiplying delta W by an integrating vector which is 1 by P in this particular case, and when I am considering delta Q, I am using 1 by 2 T. So these two are integrating factors which convert a path function into a point function basically. Now let us talk about the specific heat and latent heat part. The specific heat of a substance is defined as the amount of heat required to raise a unit mass of a substance through a unit rise in temperature. So I am considering that we have 1 kg or 1 gram or a unit of a substance, and there is a unit rise in temperature, could be 1 degree Celsius, could be 1 Kelvin also, okay, and so on. And we can represent it by a symbol small c, specific heat. So small c, you must know that Q is equal to M into C into delta T. But I know that you must have gone through the equation Q is equal to MC delta T in terms of number of moles. So it doesn't matter. Both will give you the same result. You forget about the number of moles for the timing. Here we have the mass. This is the specific heat, and this is the temperature difference, and this is the heat transfer. So from here I can calculate the value of C. C is given by, this value of C is given by Q divided by M into delta T. The unit of Q is kilojoules, mass is in kilogram, and temperature is in Kelvin. So the unit for the specific heat in this particular equation is kilojoules per kg per Kelvin. So you should always remember that. and tell me whether it is a specific quantity or a means intensive or extensive property. Specific heat in this particular case.
Sir, extensive because it depends on mass.
Listen, you can see in the denominator you have divided by mass. So, so it's an intensive property. Okay, it's
Sorry,
an
sir.
intensive property. So that means Q small c is equal to Q divided by M into delta T. Okay. Now we have two other types of the specific heats. One is specific heat at constant volume and other is at constant temperature. We have discussed about two processes, one about isochoric and other about constant isobaric, constant pressure or isobaric process. So if this heat transfer, whatever is the temperature change of 1 unit of a mass, 1 kg of mass, if it undergoes a 1 degree Celsius temperature change, and uh, it happens when the volume is constant, then that particular specific heat will be known as, okay, this I have, yeah, that will be known as CV or specific heat at constant volume. But if this change in temperature of unit mass of a substance takes place under constant pressure, then that will be represented as CP or specific heat at constant pressure. So there are two types of the specific heats. One is CP and other is CV. And both have the same units, that is kilojoules per kg Kelvin. So this is the value of the specific heat, unit of the specific heat. One more thing I would like to tell you, you should always remember that the value of CP for air, this is a very important value. CP for air is 1.005 and the value of CV is equal to 0.718. You should always remember these two values and the unit is same, kilojoules per kg Kelvin. So this is the unit actually. Okay, and you must know that if you want to calculate the R, which is the characteristic gas constant, that is given by Cp minus Cv, and for air the value will come out to be 0.287 kilojoule per kg Kelvin. Okay, kilojoule per kg Kelvin. Now, so that means it's very simple. If I want to calculate CV, then here I have to take QV, that means heat transferred during the constant volume process. If I am calculating small Cp, then I will be taking Q during the constant pressure process dividing by M into delta T. So this will be the value of the Cp or the specific heat at constant pressure. Now this is very very important for solids and liquids. However, the specific heat does not depend on the process. Okay, for solids and liquids. So in that particular case, there is no effect of the pressure actually. So here we say that Cp and Cv are nearly same. And if you will see the values for water also for the specific heat, so whether it's a constant pressure or whether it's a constant volume, you will find that the specific heat is same in both the cases. And now let us go to the next. The product of mass and specific heat, M into C, it is known as heat capacity. Okay, now it is heat capacity. So capital C is given by M into C. Okay, so this is that you need to remember. And if you will calculate the unit in this particular case, that will come out to be kilojoules per Kelvin, because now we have multiplied by mass. So M into small c is specific heat, capital C is heat capacity. So these are the two different terms which we will be using. Now latent heat, you must know that it is a hidden heat. One more thing I would like to tell you about uh, uh, specific heat. Okay, there is okay, latent heat. See, you must know about the sensible heat part also. Do you know what is sensible heat? What is the difference between sensible and latent heat? See, when I say sensible heat is basically required when we are raising or reducing the temperature of a particular substance or a body. Okay, so if we have water as a substance, we are increasing its temperature from 20 degrees Celsius to 50 degrees Celsius. So whatever is the amount of the heat which we are supplying, that is actually sensible heat, because if we are putting the thermometer into the water when it is being heated from 20 degrees Celsius to 50 degrees Celsius, we can sense this temperature with the help of a thermometer. Now take another example. Suppose we have the water is at 100 degrees Celsius at atmospheric pressure. So what I am saying? I am saying that the pressure of the water is 1 atmosphere and its temperature is 100 degrees Celsius, and it is the boiling point. So when I supply the heat, I am saying that it is water, so it's liquid. So when I supply the heat, what happens at the same pressure and same temperature, it converts to steam. So there is change of phase. Change of phase is taking place. So this is the heat which is required to change which is required to change the phase of a substance. That is actually known as the latent heat or the hidden heat. Why hidden heat? Because in this particular case, even if we put the thermometer during the time when the phase change is taking place, you will not find any change in the temperature on the thermometer. So we call this heat as the latent heat or the hidden heat, because this cannot be sensed by the thermometer. Okay, so latent heat is the amount of the heat required to cause a phase change in a unit mass of a substance at a constant pressure and temperature. So you can see I have considered pressure and temperature as constant. There are three phases in which matter can exist: solid, liquid, and vapor or gas. One is the latent heat of fusion. It is the amount of heat required to melt unit mass of a solid into liquid or freeze unit mass of liquid to solid. Then we have latent heat of vaporization. It is the quantity of heat required to vaporize unit mass of liquid into vapor or condense unit mass of vapor into liquid. Okay, and there is something known as latent heat of sublimation also. It is the amount of the heat transferred to convert unit mass of solid to vapor and vice versa. Okay, do you know any substance which directly sublimates? It is solid carbon dioxide. It is also known as dry ice, which directly sublimates into gas actually. Then there is important thing: latent heat of fusion is not much affected by pressure, whereas latent heat of vaporization is highly sensitive to pressure. So even if the pressure varies a little bit, the latent heat of fusion will not be much affected, whereas the latent heat of vaporization means during which the liquid is changing into vapor, that is highly sensitive to pressure. Okay, but it may not be required for your studies actually. If you are not from mechanical engineering, if you are from mechanical engineering, you should remember this. Now few points. What is the time right now?
140.
148.
148.
Okay, we have 12 minutes. Okay, so points to remember regarding heat and work transfer. We have discussed about heat and work transfer extensively in this particular chapter. So these are very simple things: heat transfer and work transfer. So you can see we are always writing heat transfer and work transfer. We are not writing heat or work. So always remember, whenever you are writing, you have to write work transfer. Whenever you are writing heat, you have to write heat transfer. These are energy interactions. A closed system and its surroundings can interact in two ways. One is by heat transfer and other is by work transfer. So basically, whenever you have a thermodynamic system and there are surroundings here, so if this is system, so these two can interact with the help of work transfer or heat transfer. So W and Q. With the help of W and Q, the system and the surroundings interact. Okay. Thermodynamics studies how these interactions bring about property changes in a system. So it's quite easy. If there is work which is entering into the system, naturally the pressure, volume, and temperature will change, or other properties will vary. Similarly, when the Q will also be either leaving or entering the system, the properties will change. The same effect in a closed system can be brought about either by heat transfer or by work transfer. Whether heat transfer or work transfer has taken place depends what constitutes the system. Okay, so that means it is not necessary that if you have to bring a system from a particular state 1 to particular state 2, you require either heat transfer or work transfer. Means if you have heat transfer only then also you can take the system from state point 1 to 2, or if you have only work transfer, then also you can take the system from state point 1 to 2. Okay, or even if you have both the things, then also you can go from state point 1 to 2. So anything is possible in this particular case. Both heat and work are boundary phenomena. Both are observed at the boundaries of the system, and both represent energy crossing the boundary of the system. So these are boundary phenomena. So this is the boundary here. Okay, this is the boundary. So work transfer and heat transfer will be observed only when crossing the system boundary. It is wrong to say total heat or heat content of a closed system. Okay, heat is in transition only. Heat transfer will be observed only in transition, because heat and work is not a property of the system. Heat, like work, cannot be stored by the system. Both heat and work are energies in transition. I have already told you. This is very important. Heat transfer is energy interaction due to temperature difference only. All other energy interactions may be termed as work transfer. Both heat and work are path functions. Told you already, inexact differentials. The magnitude of heat transfer or work transfer depends upon the path system follows during the change of state. Once again, these are the repetitive things. Okay, so this was about the work and the heat transfer. I have sent you one tutorial sheet. So you try to solve those problems and try to do that. Let us see whether you are able to do it or not. And moreover, if you have the book by P.K. Nag, okay, if you have the book by P.K. Nag, whatever the examples are given in this chapter on the heat and work transfer, and there may be some questions in the exercise. The tutorial sheet which I gave you is from the exercise only. Okay, so what you have to do, you have to do these examples also, and you have to do this tutorial sheet or exercise also. Okay, तो ये सब करना है आपको, एग्जाम्पल्स और एक्सरसाइज अगर नहीं करते तो आपको ट्यूटोरियल शीट करना है. ओके, जो ट्यूटोरियल शीट आपको मैंने ग्रुप के ऊपर भेजी है उसको पूरा करना है. नाउ so basically now we have done 3 chapters, chapter number 1, chapter number 2 and chapter number 3. Okay, so I hope this chapter is clear to you. Now I will give you some idea about the first law of thermodynamics. Now as I have told you, energy is of two types. One is the energy in transition. So energy can be in two forms: energy in transition like work and heat transfer, which are observed only at the boundary of the system. Okay, and secondly, it is the energy in storage, where energy is stored macroscopically by virtue of motion, position or configuration of the system, or microscopically in the molecules or atoms constituting the system. So this is the energy in storage. Second type. The first type is energy in transition, and we have discussed about the energy in transition, which is either heat or work. Now what is first law of thermodynamics? I told you today also. First law of thermodynamics is sometimes known as FLT. So FLT is basically conservation of energy principle only. In simple words, we can say that energy can neither be created nor be destroyed. So this is first law of thermodynamics. But actually this is you can say either a 10th class or 11th class definition. Now we have to think about different type of the definition. The definition is actually according to first law of thermodynamics in a closed system. Okay, so see the terms which are written in the definition: in a closed system. So we are talking about the closed system. undergoing a thermodynamic cycle. So the system is undergoing a thermodynamic cycle. The cyclic integration of heat transfer is equal to cyclic integral of work transfer. So mathematically, what I want to say is cyclic integral of delta W is equal to cyclic integral of delta Q. And this is valid when we are taking consistent set of unit. Consistent set of units. See, actually, previously we were using MK system of units. So you must be knowing that in MK system of units, the unit of heat transfer is calorie. Whereas in for work transfer, we were using some other unit, kgf meter, something like that. So for there you will not be using this particular expression there. There have you need to have a some j value also either on left side or right side. I don't remember now because I have not used it for a long period of time. Okay, so when we talk about the SI system of units, work and heat transfer both are in joules. So we can directly say that this value cyclic integral of delta W is equal to cyclic integral of delta Q actually. So this is what is the first law of thermodynamics when the system is a closed system and it is undergoing a thermodynamic cycle. So what is the time right now?
156.
156.
156, sir.
156. Okay. So 1 minute more. Now you can see it here. What is the meaning here actually? You can see. So first law of thermodynamics is this one, cyclic integral of work is equal to cyclic integral of delta Q. What does it means actually? So what I have shown here is I have taken a PV diagram and I have shown a cycle which is in the form of a triangle. So this is the first process 1 to 2, process 2 to 3 and process 3 to 1. These are the three processes. So how we can write this particular first law of thermodynamics for this closed system? Okay, you know cyclic integral denotes this symbol actually denotes the cyclic integral for the closed path. This is the first law for closed system undergoing a cycle. Okay, you should always remember this. It is accepted as a general law of nature since no violation of it has ever been demonstrated. Now when we apply this FLT to the cycle undergone by a thermodynamic closed system, so this is the first statement that we can write, or we can also write it as in this manner. Sigma W for the cycle is equal to sigma Q for the cycle. And that is the meaning here is that heat transfer for the process 1 to 2 plus heat transfer for the process 2 to 3 plus heat transfer for the process 3 to 1 is equal to work transfer for the process 1 to 2, work transfer for the process 2 to 3 plus work transfer for the process 3 to 1. So this basically, this when I am saying that I am using this particular equation for this particular cycle, then the meaning is this one. So I have considered the heat transfer for all the processes, added them, and that is equal to the work transfer in all the processes, and I have added them. Okay, so that is the meaning of the first law of thermodynamics. So once again, this is the equation. One line I will read. The first law of thermodynamics owes much to J.P. Joule, who during the period 1840 to 49 carried out a series of experiments to investigate the equivalence of work and heat. So it was J.P. Joule who have worked for first law of thermodynamics. Okay, so this is where I will end my lecture today.